going on inside your cells, your little powerhouse in your mitochondria to, flies, weather, and all these physical and chemical properties like boiling point elevation and things that we've studied. They all happen naturally, so that means their Gibbs free energy has to be positive or negative for that process. Has to be negative. Yeah. So kind of a simple idea, but it's really powerful. So here's an idea. Let's apply this Gibbs expression to the process of a stretched rubber band. And the idea here is to get some inkling of the ambiguous term, right? The entropy. What will be the change in entropy when you contract a rubber band? So you have a little rubber glove. The idea here is contraction would be, it's starting out expanded. So contraction would be that, right? So let's pick on Danielle here. Okay. That's the contraction. Is delta G for this process must be what? What's now remember, if something happens naturally, delta G is negative. So can you stop this from happening? It contracts. There's nothing you can do about it. So delta G has to be, everybody has to be negative. Okay. So delta G is negative. Okay, so that's negative. So we'll have a negative number here. Right? So we're just trying to figure out what happens to that delta S. Okay. After stretching rubber band, it feels. Now this part's kind of hard to do. You can stretch it and try to feel it, or put it on your finger and stretch it, right? But if you play around with it a little bit, doesn't it feel warm when you stretch it? Okay, so here it is. It feels warm. I agree. So stretching a rubber band, Diana, must be exo or endothermic. If it feels warm, you stretch that guy and he feels warm. It feels warm, so that means it's got to be producing heat or absorbing heat. If it feels warm, right? Right? It feels heat, so it's producing heat. That's why it feels so warm. So if it's producing heat, it must be exothermic. Okay. So stretching a rubber band is exothermic. Therefore, contraction of a rubber band, Crystal Munoz, must be. So stretching a rubber band is exothermic. So the opposite, contraction, must be endo, right? Endo. Okay. So we put a sign. So we're talking about contraction. So contraction, endo. Okay. Oh, I just answered it. So for contracting rubber band, everybody, delta H must be positive. Okay. Now look at the expression. Jasmine. So we've got delta G has to be negative. Delta H has to be positive. Therefore, delta S for contracting rubber band must be, to make this work, what does delta S have to be? You want a negative number for delta G. Delta H has to be positive. Delta S then has to be what? Otherwise the math won't work. Well, if it's 0, then you have a negative number equals a positive number. So that won't work. It can't be 0. Negative. It has to be negative. If you put a negative in for the delta S, you multiply it by that negative t thing, you get a positive. Add it to a positive, you still got positive. So that ain't it. It has to be positive. Delta S has to be positive. It is kind of, right? So positive times a negative, right, is a negative. Add it to it. It must be a huge positive number, right? This thing has to be a big positive number because it has to override that delta H. And this really isn't very typical. Usually why things are so natural and why they occur spontaneous is because they're exothermic. They produce all this heat. And that's what makes delta G negative. But not in this case, not in the case of a contracting rubber band. So if delta S is positive, what does that mean? Well, the pictures are trying to tell you what that means, right? When the rubber band is stretched, here's the energy interactions, right? They're pretty much lined up, right? And then when it contracts, man, it's a big jumbled mess. So upon contraction, Alyssa, what could you generally say? Upon contraction in a rubber band, the energy in the rubber band becomes more, right? Because here they're kind of ordered. Now they're, geez, all over the place. So that's a dispersed means. Yep. Spread out. So entropy, I like this example of entropy because a lot of, I think often the conception of entropy is, you know, how ordered things are. Well, yeah, that's right, but it's really how ordered the energy is. That's really what entropy deals with. Okay. Interpretation of free energy. Derixa, when delta G for a process is, then the process can be used to do work. Yeah, less than 0 because it'll happen, right? Explosions happen. You can't stop them. They're just spontaneous. They're natural. So you could get that explosion to move a piston and move a car or something, right? How did we say physicists define work? Tegan, how do we say they did that? Yeah, so something has to move. So I don't think that's even in the homework, but I don't know, I just feel like it has to be there. Calculating a thermodynamic equilibrium constant. Danny, before, we were doing all these equilibrium constant expressions, right? And we said K was what over what? Products or reactants. And then we always wrote these brackets. For Sabina, what the bracket's supposed to mean? There's the C, the concentration. In units of, well, that's the first one. In units of molar, big M. Okay. But we were lazy. It's just like for ions, they're supposed to write AQ. When we had this equilibrium constant, we were supposed to put a little C down there. A little C for, probably, maybe, for, they're all brackets, concentration. We should have been writing a C on that this whole time. Because now they're saying, because that's what it was KC, equilibrium constant expressions in terms of concentration. Well, we were kind of lazy. That's okay, I guess. All right? But now they're saying, okay, no C. In thermodynamic equilibrium constants, that's what K is with no C, the thermodynamic equilibrium constant. So in thermodynamic equilibrium constant expressions, all concentrations are in units of, what would you guess, Monica? They're all in units of, they're just going to keep the same thing. The difference is going to be the next part of the sentence. So what units are they going to use for concentration? Molar, molarity. They're going to stick with it. Except for which state, Gabby, are they going to say, oh, no, can't use concentration? Oh, solids. Do solids ever show up in any equilibrium constant expression? No, solids don't. What else doesn't? Liquids. So it can be a KW, it can be a KSP, it can be a KC, it can be a K, it doesn't matter. All equilibrium constant expressions, they don't have solids and liquids, so we can pretty much rule those two out. Well, it leaves a 50-50 shot. Gases. Gases. Okay. Which are in units of. Danielle. What units do you think they're going to say? Oh, this is what it all has to be in. What are some units of pressure that you could guess at? There's PSI, but that's too British. It's not that one. ATM. It's ATM. Okay. Atmospheres. So, and they want that pressure to be in atmospheres, and it's got to be the partial pressure. Well, let's see if we remember what the heck partial pressure is. Diana, in this room, let's say this is our room. What gases are in here? Oxygen gas. What's another gas? Anybody? Nitrogen, like 77%, I think? Or 71%. 71%. Another gas. Yeah, carbon dioxide. Probably some water vapor, right? In this room. Okay, well, the whole room has a pressure. It's probably a little bit less or a little bit more than 1 atmosphere. What would you guess? A little bit less. Why? Because we're not at what level? Sea level, right? We're a little bit higher, I think, aren't we? We have to be. So since we're a little bit higher, we'll have less than 1 atmosphere. So perhaps the pressure due just to the nitrogen gas, maybe the total, well, the total would have to look like this. Nitrogen, oxygen, CO2, water, right? All those partial pressures added up. So all those partial pressures have to add up to be whatever the total pressure is, a little bit less than 1 atmosphere in here. Okay. But how could you calculate just one of them? So that's how you get the total. But how could you calculate just one partial pressure? The ideal what law? Gas law. Ideal gas law. Okay. Let's say we want to calculate just nitrogen. So you put in a little subscript for nitrogen. There's only one other place you're supposed to put the subscript nitrogen on, and then you can calculate it. The little n. And what was little n?
Moles.
The moles of the gas. Just the moles of the gas. So that's how you could calculate it if you wanted to. That number is this. Okay. That number, that partial pressure, is what we're going to put in the thermodynamic equilibrium constant expressions. Okay. So, a relation between Gibbs free energy and the thermodynamic equilibrium constant. It's given below. So I give you this, right? How did we get this in the first place? Yeah, tables, right? Products minus reactants. So I'm sure this is going to be a homework question. They're going to give you a reaction. They give you all the delta G's. You find delta G0, products minus reactants. Then they say, hey, what is the thermodynamic equilibrium constant? Well, all I do is give you this equation. You have to know how to solve for K. So, yeah, good question. What I think is easier, though, is what someone did last hour. And what they did is they put in all the units for everything. You'd have a number there, negative, a number here, right? Put in the numbers for everything, right? And then divide one side by the other. You end up with a natural log of K is some number, whether it's positive or negative, right? You know, if it's negative, put in the negative sign, fine. Then what do they do to both sides? Raise it to the e power, exactly, right? E to that number. would be my K, right? Because do you remember doing this kind of thing? Like, raise both sides of that E power. And these guys are inverse, so they cancel out. So you have to know how to rearrange this stuff. But I think it's easier how she did it. She just put in all the numbers and then got it to work. Now, when you put in all those numbers, there's a trick to it, though, Crystal Munoz. Do you remember what units were delta G0 in those tables? What units were they in? Kilojoules per mole. Okay. Now, there's a lot of different gas constants. That R, do you remember the R? Same R as the one that's right here, except I bet you're going to want to pick a different one. When we did this one, we picked 0.0821 liter atmospheres or mole Kelvin for our R. You don't want to use that one here. I don't know. Anyone read the small print in the quizzes to see a different value for R? First number was an 8. You probably never paid much attention to it because you didn't need it. 8.314. What's important, though, are the units. Joules per Kelvin mole. So do you see a problem here, Diana? Table units, R units. Yeah, it's kilojoules. So you got to pick one or the other. Either convert this guy to joules or convert your R to kilojoules. Otherwise, you're going to get the wrong answers every time. So make sure your units are consistent. Okay. Delta G and delta G0. Well, it looks to me, Jasmine, the only difference is this little circle. What's a little circle mean? Give you a hint. STP. It's not oil. Standard temperature and pressure. Okay, standard temperature, 0 degrees Celsius. Standard pressure. Man, if you get this right, I'll automatically ace you on the quiz. Because I learned something this morning. Because what standard pressure? You don't want to guess first? Standard pressure? That's the best guess that you could make, right? But it's wrong. NIST, the National Institute of Standards and I forget. They changed it. 1 atmosphere is not metric enough. They changed it to 0 degrees Celsius, great, or 273 Kelvin, and 10 to the 5th pascals. But pascals, that's the metric unit for pressure. But this is really close to 1 atmosphere, so let's just stick with this and we'll be good. Okay.
Should we get an 8?
She gets 1 atmosphere. You have to guess 10 to the 5th pascals. Okay. I know, that's a good question. I don't know. Maybe I've been wrong for years. But it's really close to 1 ATM. So they might have changed it a long time ago and people just don't care. Calculating free energy at different temperatures. So the difference here is the temperature. This one's at 0, the other one's not. So you just calculate it. You want to change the temperature, just calculate it. So T will be our new temperature, but in what units, everybody? Has to be in Kelvin. And where do we get these two? From the chart, exactly. Tables. Product minus reactants. Plug in the new temperature, and we can get a good guess for what the Gibbs energy change would be at that temperature. Okay. Here's some questions. So you want to go to the boards, or are you going to be lazy? All right, well, the first two are the good ones to do at the boards. We'll just leave you alone. Fine. Give the expression for the thermodynamic equilibrium constant for the following reaction. So since I can't see you do it, Tegan, you're going to have to tell me how to do it.
Oh, just the expression? So
Yeah.
it's like K equals concentration in G2 plus concentration OH negative squared over 1.
Ooh. Everybody agree? All right. How about 60? Sabina.
So K equals brackets H3OH.
Okay, but something's messed up already. CH3OH is methanol, by the way. But methanol is a what state? It's a gas. So we can't use brackets. We're supposed to write what? What do we call it? The what pressures? Partial pressures. All right. So what was our way of doing that? So this is how you write the partial pressure of nitrogen. How would you write the partial pressure of methanol? This, but yeah. So Sabina, how would you do that? A big P, subscript. Good. And now the bottom part? Oh, let's ask somebody else the bottom part. Monica, how would you do the bottom part? No, just tell me. Big P, CO, big P, and squared. Yeah, just like you're always multiplying on the bottom and top, right? Those equilibrium constant expressions. Okay. I added the table because I got tired of handing my book around. So what is the standard free energy change at 25 degrees Celsius for the following reaction? To obtain necessary information from Appendix C. So that's what I did for you. So Gabby, what's the game plan to do that? What would you do? Oh, we could do it that way, right? See what she's saying? If you get paid by the hour, this is a good way to do it, right? Products minus reactants for delta H0. Products minus reactants for delta S0. Multiply it by T. Now T has to be what Kelvin probably in this? It has to be in Kelvin, but what number would you plug in for T? 273 plus 25. All right, so that'd be 298. So that's a lot of work. Be a lot easier to just do what? Use the delta G. Products minus reactants. But they would both give you the exact same answer. Right? So go ahead, see if you can get that. And then go on to part B and get the thermodynamic equilibrium constant. Watch your units. Products minus reactants. See how what Gabby said would really work. But since I gave you the delta G0 ones, you might as well use those from the beginning. So it's delta G0 of the products minus delta G0 of the reactants. they're just zeros, right? Now, to give you an idea, when you calculate that thermodynamic equilibrium constant before you go and start working on that, should you expect a big positive number or a very, very small equilibrium constant? Big and positive, why? Because delta G is negative. So that means it's very natural, very spontaneous. It's going to happen, and it's going to happen a lot. So you should have a lot of product. So K should be huge. So if you do this right, you should get a big answer for part B. So remember your expressions. And I think it's easiest if you plug in the numbers first. You can do the algebra first, solve for K, and it works. But I think it simplifies things if you put in the numbers first.
So how do I change my R to joules?
You know what I think is always easier to do, Drixa, is what does kilo mean? Kilo means 10 to the third. Milli means 10 to the negative 3. Kilo means 10 to the third. So I could just write negative 108. Instead of writing kilojoules, just write times 10 to the third joules per mole. You don't even have to do the whole box thing. Just remember what kilo is. Times 10 to the third
That's
joules per mole. No, I just put it in joules per mole because that's what my R is in. And it looks kind of funky because it's not correct scientific notation, but your calculator will take it. Just put 108 and then exp 10 to the third.
All we have to do is multiply by 10 to the third every time.
Well, for kilo, because it's whenever you see kilo, just write in 10 to the third and erase the kilo. If you see milli, write 10 to the negative 3. If you see centi, 10 to the negative 2. What was another one? Deci, 10 to the negative 1, right? Deci, 110. That works every time. It looks kind of ugly, but it's... Yeah, so get... Oh, I forgot my T, didn't I? 298, yeah, I got to have that in there. So then, get a number for the natural log of K. And then just raise both sides to the e power. Right, so divide negative 108 times 10 to the third, divide it by a negative 8.314, divide it by 298, get a number over here. Then raise it to the e power. And that's orange on the calculator, so you have to do shift first. I got 43.6. Oh, is that what you got? Yeah, I got about 43.6. Now you have to raise both sides to the e power. right? So e to the 43.6 has to equal e to the natural log of k, but those guys cancel out. So, did you get a huge number? I got about 8.5 times 10 to the 18th, so it's huge. It should be.
How do you raise it?
So, you have 43.6 in the calculator? Okay, and then do shift that one. Since e to the x is orange, you have to push shift first. Okay? Okay, if you got it, go on to the next one.
Okay, I got it. But then do I divide this in?
So you have to take this, divide by this, and then divide it by that. So just have this in your calculator. Hit divide by this, hit equals,
But I thought
then
you
divide by
wanted us
that.
to times this and then that number.
Why? You're doing extra steps. You're not getting paid by the hour. Take this, divide it by that, then divide it by that. I mean, you can, Drake, say you're fine if you do that, but it's just extra work.
I just look at the calculator, so I got to that equals L and K. So then,
Oh, could you put everything in kilojoules or what? This is joules. So I have 43.6 equals LNK, not 0.04. 108 times 10 to the third, divide by this, divide by that. Yep. Divide by 8.314. Divide by 298.
oh no, it's because I have that.
Wait, did you get 8.5 times 10 to the negative 18?
8 positive 18.
How did I get that?
So in this one, pretty much all they want you to do is find delta G at that new temperature. Remember the equation for that?
I don't even know how I got here.
Delta G was delta H0 minus T delta S0. That's the equation that you have to use to find G at different temperatures. That might even have had a little subscript on that delta G to show you that, yeah, you pick a temperature, and then you can calculate delta G at that temperature. But anything with a superscript 0 on, you can use table. You have to use the tables. So you're going to have to use the tables to get delta H0, use the table to get delta S0. And watch those units, because look, they're different. Then plug them into your expression here. Make sure you have T in Kelvin.
So for delta H to solve, we use the delta H values.
Products minus reactants. So yeah, so 2 times a negative 36, oh, minus 0.
So this one's kind of the same thing?
Yeah, except we don't have to calculate K, thank goodness.
Oh, you don't?
It didn't ask us to, so.
How do you know when it asks? Oh, I see, I see what you're saying.
Mm-hmm.
It's -36.
Oh, thank you. Thank you, young lady. That should be worth a brownie point.
I got a jump. Hey, working by the hour. I'm just kidding.
And 152. All right, and watch your units. This one's in joules per mole, the other one's in kilojoules per mole. Hopefully you get, I think last class got negative 218, so I think that's right. If you get negative 218, go on to the last question. Maybe you can knock them all out. This one isn't in kilojoules, though. This one's in joules. That's probably
This is in kilojoules? What?
delta S. The delta S table, it's in joules per mole. So just move it over 3 places. That'll be 0.115 kilojoules.
See?
Mm-hmm. Kilojoules.
Oh,
Because it was joules. That made it kilojoules.
I can't get that.
You're not getting it? Now, when you did your delta S, yeah, because he's in joules. So
But I changed it.
this one was 72. Oh, you changed this. Oh, you went the wrong way, I think. Because delta.
Is it -3?
You don't do delta G.
Yeah.
You're doing delta H. So 2 times a negative 36 is negative 7. Oh, that's positive 3, right? Kilo is 10 to the positive 3.
And then I multiply these two and I
Yeah, and
Subtract?
subtract from that. Just take this minus that times that, and you hit equals. Should work.
How'd you get 200 whatever you said?
Negative 218.
Yeah,
Probably where you're messing up is the delta S.
I was not messing
So negative 72 kilojoules per mole. That's that one. Minus T has to be 1273 times delta.
1273.
This is 1,000 degrees Celsius. So T has to be 273 plus the temperature.
Oh, okay.
I looked it up.
You get it to work now?
No.
No.
I'm still not getting
I have it set up right here, and then.
Oh, this is times 10 to the negative 3.
Oh, I did that like.
Now, if you want,
negative
because if you want to leave it in joules per mole, great. Then make this one times 10 to the 3, because kilo is 10 to the 3.
So what do we want? Well, we have to get in kilojoules, right?
Either one, you can pick your. Well, my answer's in kilojoules.
So
So your delta H was negative 72, everybody?
Yeah.
Okay. And your delta S was 115.
And then you just convert that to kilojoules.
So you have a couple choices. You could have delta GT. I think just joules is easier, but we'll put everything in kilojoules because that's what the answer's in. Negative 72 kilojoules per mole minus 1273 times 0.115 kilojoules per mole. And we'll get the right answer, negative 218.
And if you left it in joules, what would the answer be?
It should be negative 218,000. No, even more. Yeah, negative 218,000. Because you'd have negative 218 times 10 to the third. So come by if you have some questions.